Section 1.5 is about function notation. So we talked a lot about, is this equation representing a function or not, why, and so forth in the last section. Now we can talk about function notation, where we use f and then of x is equal to y, as we've been using it before. So in this context, you can think of f as just representing that this is a function. That is it. That is a function. X is still our input, and y is still our output in this. Now, the thing that I need you to get used to with this is that these parentheses here are not corresponding to multiplication. They're literally saying that this is a function of x. So you need to start translating that in your brain now. This is not multiplication. F of x is saying f function of x. So f is telling you function, the parentheses are telling you that it is a function of the variable that's inside those parentheses, which in this case is x. An example of using this notation is if we take a look at our equation y equals 3x plus 2. So if I ask you, is this a function? This is reviewed from 1.4. Is this a function, right? If I substitute in a value for x, do I get one value for y and only one, or do I get more than one? And in this case, you should only get one because it's linear. It looks like the linear functions we talked about already. So that would mean, yes, it is a function, right? So we can write it as f of x is equal to 3x plus 2. This is how we're going to use the notation. So the natural next step is to look at evaluating these functions at particular values. So before we might have asked, what is y when x equals 2? And you would have substituted that into the equation. Whereas now, if we're talking about functions, we can talk about it as what is f of 2? What is our function evaluated at 2? Or in the same context as the earlier question, what is f of x when x is equal to 2? So for the equation where you had y equals 3x plus 2, so we can just look at that real quick. We've talked about this a little bit already. In order to determine what y is when x is 2, we replace each x with a 2, right? And so that is going to be 3 times 2 plus 2, which if we simplify will get us an 8, right? And since f of x is equal to y, we should get the same result for f of 2 or for, right, f of x when x equals 2, which is the same thing. So if I took a look at f of x, which is also equal to 3x plus 2, then I'm going to do the same thing. F of 2, I just replace every x with a 2. 3 times 2 plus 2, which if I simplify, again, gets me an 8. So we're doing the same things, you're just changing the notation. Recall at the end of 1.4, we described these equations in 4 ways. And so in this case, what is the function doing? If we describe it in words, it is going to multiply by 3 and then add 2. Right? That is a statement of what this equation is doing to x, right? So what would the function be if I added 2 and then I multiplied by 3? Right, if I'm adding 2 first, then that whole thing needs to be multiplied by 3. So the function that would correspond to this equation is going to be given by a 3 times the quantity x plus 2, right? Quick aside, some vocabulary. We have talked about this in class a little bit, but we haven't really talked about it in the context of functions and function notation. So our independent variable, right, that was our input. That is still x. Our dependent variable is still our output, which in this case is the function of x, whatever that is, right? Net change in the context of the function notation can be evaluated from some values of x, a, and b as the function evaluated at b minus the function evaluated at a. Okay? And that would be for some x values b and a, respectively, where b would be greater than a generally, or at least later in the data set, which is the same. So let's do an example of determining net change with a function. So if we use the same one that we've already been using, f of x is 3x plus 2, we want to evaluate this from x equals 0 to x equals 2. Net change is the bigger one minus the smaller one, right? So we need to determine first what is f of 0, right? F of 0 is going to be, we replace all the x's with zeros, 3 times 0 plus 2. Okay, so that's 0 plus 2, or 2. What is f of 2? Again, replace each x with a 2. 3 times 2 plus 2. So that gets us our 6 plus 2 again, getting us the 8 that we found earlier. So if I'm looking for net change, right, as we discussed, is going to be f of b minus f of a. And in this case, right, b is the larger one, a is the smaller one, so f of 2 minus f of 0. It's basically going to be the current one minus the last one in some sense. So if we're going from 0 to 2, then we're at 2. So it's going to be the 2, f of 2 minus f of 0. And in this case, that would be an 8 minus a 2 to get us a net change of 6 for this particular function. Now we want to talk about domain in the context of a function. When we talked about domain in the context of data, it was just the specific data points. So now when we're talking about domain of a function, we're looking for, are there any values that I cannot use for this function? So if you take a look at an example, this will make a little more sense. If we have f of x is equal to 3 over 1 minus x, are there any values of x that I can't substitute into this equation? That's the question that you want to ask yourself for domain when we talk about functions. And at some point you probably learned that you can't divide by 0. If you divide by 0, things blow up. It's very, very bad. So what we would do here is we would determine, okay, well, x cannot equal 1. So I have to exclude, right, if I write that mathematically, that's x not equal to 1. And that allows me to then say, okay, so are there any other values? No, that's the only one that I can't substitute in. Everything else will be defined. It'll give me a value for f of x. So that's the one that I have to exclude. The way we write this is in something called set notation. And you use the squiggly brackets again. So you're defining values of x. We use this vertical bar to add exclusions. So effectively the x is saying all values of x, but not this one. So this vertical bar, if you took a whole lot more math, it stands for the words such that. It's basically saying all values of x such that x is not equal to 1. So it's giving the additional constraints to that set. So that's an example where you have to exclude a value, but let's take a look at the linear function we've been using all along, right? 3x plus 2. Is there a single x value that you cannot substitute into this function? No. All values of x work. So what that means is that when we define the domain, you can write it in one of two ways. You can say that the domain of f of x is given by just x. No exclusions, no vertical bar, because we're not taking anything out. Just all values of x. Or you can just write the words all values of x. One more example. What about the square root of 2 minus x? When is there a value I can't substitute into a square root that's not going to work? Earlier you should have, from a previous course, you should have learned that if you substitute a negative value in there, you won't get a real value out. The square root can't evaluate the negative square root, or the negative value. So that means that you need to ensure that the interior of that square root, the 2 minus x term, needs to be greater than or equal to 0. Which, if I add x to both sides, will get me 2 greater than or equal to x, which means that my x, if I just mirror flip this whole thing, I would say x is less than or equal to 2. I like this phrasing a little bit better, but this statement is completely fine. 2 greater than or equal to x. So basically, as long as x is less than or equal to 2, we're good, right? So then I would write my domain as the set of x values such that x is less than or equal to 2. That's all you got to do. The last big concept in this section is piecewise defined functions. This builds upon the concept that we've been talking about with domain. We've been talking about how to define our domain, and piecewise defined functions actually define different functions on different parts of the domain. So being able to define a specific section of domain and understand what that means allows you to then correlate that with the specific function appropriately to determine a function value. Let me give you an example. So, right, if you think of it in terms of something you might actually encounter, right? If you bought a new tablet and that cost you $79, and it came with a prorated 4G package that was $5 a month for the first 3 months, but that was after the first month, so your first month is free, then it would be no longer prorated after those 4 months had passed, so you would have $15 a month after that. What would be the total cost that you've spent on this tablet and its 4G package after X months? Okay? This is a piecewise function because there are different rates during different months, right? The first month, you're not having to pay for anything extra. You just pay for the tablet. The second, third, and fourth months, you're paying $5 a month in additional fees towards the tablet. And then any month after those 4 months have passed, you have to pay $15 a month for that 4G package. So, if our domain is in months, which it is, it has to be divided so that the correct rate is added in those months appropriately. So we have to model this with a piecewise function, right? So I write f of x is equal to this big squiggly bracket because I'm going to have more than one thing that it's equal to. Okay, this is important because there's more than one equation here, really. It's just that each equation corresponds to specific domain values. So the $79 is only going to happen within that first month. So you just bought it, no months have passed yet, you spent the $79 though on the first day that you got it. So that goes from 0 to 1. Because the entire first month, that's all you had to pay for was the tablet. The first month of the 4G package was free. Nothing else was added. After that first month has passed, right, so I'm saying when x is greater than 1, change color. So if x is greater than 1 but less than 4, because that's going to happen for 3 months, 1 to 2, 2 to 3, 3 to 4, on that domain, then I have the $5 per month, and I have the $79 that I've already spent, right? So we have 5 times x minus 1 because I only pay it once per month, right? So when x equals 2, only 1 month has actually happened where I've had to pay for it. So it's x minus 1. 2 minus 1 gets me the 1. 1 times 5 is 1 month. Hooray, it's consistent. So the $5 hits first at month 2, which is when x is equal to 2. Finally, after those months have passed, then you have, so after that 4th month has passed, then you have to account for the $15 per month. But you also have the 3 months that you spent $5 a month. So you have to multiply 3 months times $5 per month, cost me $15. So I add the $15 here, and then I still have the initial 79. The 15 is multiplied by an x minus 4 because when x is equal to 4, which is not happening yet, that was still the $5 per month. So I don't pay the $15 in the 4th month, I pay it after the 4th month. So the 5th month is the first one that it actually hits. Plus the 15, plus the 79, and I define the rest of the domain, right? Anything after 4 months is going to correspond to this equation, okay? Okay, great. Now we have the equation. What about evaluating it? So, what is, say, f of 3? Okay. Alright. Is 3 between 0 and 1, the green underlined section? No. 3 is not between 0 and 1. So I go to the next one. Is 3 between 1 and 4? Yeah, 3 is between 1 and 4. Cool. Okay. So then I use the equation that corresponds to the yellow underline here. I substitute a 3 in for my x, so I have $5 times 3 minus 1 plus the $79 to determine what I would pay at the 3rd month. 3 minus 1 gets me a 2, so that's $10 plus $79, and that is going to get me a lovely $89 total. So after 3 months with this, I will have spent $89 on that particular tablet. Now, what if I want to look at, say, f of 6, maybe? See how much I spend after 6 months? Okay, so is 6 between 0 and 1? No. Is 6 between 1 and 4? No. Is it bigger than 4? Yeah, 6 is bigger than 4, right? Okay, we're good with that. So I'm going to use the one that I underlined with red. So I have $15 times 6 minus 4 plus $15 plus the $79. Alright, 6 minus 4, that's a 2 times 15 gets me $30 plus $15 plus $79. Alright, so that's 45 plus 79 is going to get me $124. So, going from month 3 to month 6, I had spent $89 after month 3, and I'm up to $124 after month 6. That's starting to add up pretty fast once you're paying $15 a month for the 4G package, right?